Welcome to a channel fueled by a ceaseless quest for answers to the deepest questions, including the nature of reality and the meaning of existence. We often explore quantum mechanics, entangled particles, and field fluctuations in our quest for a deeper understanding. However, we also occasionally venture into philosophical and metaphysical realms, contemplating the possible meanings behind everything while staying grounded in the principles of physics. If this aligns with your sense of adventure, buckle up and let's get started. In this docuseries called Decoding Reality, we explore many unseen aspects of our universe that offer insights into the nature of existence and its possible meaning. Today, in Part 1, The Quantum Structure of Reality, we explore hidden structures, layers, and scales beneath reality's familiar surface, uncovering a universe shaped by fields, fluctuations, and forces that are more fundamental than matter itself. We start by thinking about what reality is and what it isn't. Before we can fully grasp the nature and structure of something, it helps to first imagine what it would mean if that thing didn't exist at all. If we try to envision the concept of nothingness, the giant void serves as one of the best analogies we can find in the universe. This vast region, located in the constellation Canes Venatici, is one of the largest known cosmic voids, with some studies estimating it to be over 1 billion light-years across. Now envision yourself suspended in the center of that void. You might see only a faint glimmer from a few distant stars or galaxies, if any at all. In this blackness, you are surrounded by a near-perfect vacuum. Aside from your body and spacesuit, your 5 senses perceive pure nothingness, at least until you run out of oxygen. But this perception of nothingness can be misleading. Even in the most desolate corners of the cosmos, space is not truly empty. It is filled with subtle, invisible phenomena, quiet frameworks that shape everything, even without matter or light. These include gravitational fields, quantum fluctuations, and virtual particles. What are these invisible somethings that fill even the darkest voids of space? One way to grasp reality is through 8 interwoven, elegantly structured frameworks. These aren't merely layers stacked atop one another. They represent levels of structure, interaction, and influence that define what exists, how it behaves, and how it can change. Although we won't explore every layer in detail in this episode, we'll use a straightforward yet meaningful analogy, the systems of the human body, to demonstrate the part each of these frameworks plays within the universe. Mathematical structure is like DNA. It encodes the form and function of reality. Just as DNA organizes biological life, mathematics organizes the universe, shaping its patterns, behaviors, and possibilities. Without it, there would be no structured potential, only undefined possibility. Symmetries and conservation laws are similar to homeostasis. They keep internal balance by regulating things like temperature, blood pressure, and electrolytes. Just as homeostasis maintains order within living organisms, symmetries and conservation laws keep the universe consistent, making sure energy, momentum, and charge stay stable across time and space. Without them, reality would lose consistency and unravel into chaos. Information functions like the nervous system, coordinating signals throughout the body to manage processes such as movement, where all components must work in harmony to produce meaningful results. In the universe, information plays a similar role, governing the flow of cause and effect, encoding states and enabling systems to interact in organized, purposeful ways. Without it, the universe would lack coherence, logic, and structured interactions. Space-time is like the skeleton. It provides the framework that supports and shapes everything that moves. Just as the skeleton provides structure and guidance for the body, space-time creates the framework that determines the positions, motions, and sequence of events in the universe. Without it, there would be no where or when for events to occur. Quantum fields are like cells, the fundamental units of structure and function, too small to see but essential to everything. Just as cells produce tissues, organs, and life itself, quantum fields generate particles, forces, and the fabric of the universe. Without them, particles would lack a foundation. Only potential remains unfulfilled. Energy is like metabolism. It converts inputs into motion, heat, and change. Just as metabolism powers life by turning nutrients into usable energy, energy drives the universe's dynamics, fueling stars, movement, and transformation. Without it, the universe would stay still, motionless, and inert. Forces and interactions are like synapses. They enable connection and change, supporting bonding, reactions, and movement. Just as synapses help neurons communicate and coordinate complex actions, forces and interactions allow particles to connect, structures to develop, and the universe to progress. Without them, only separation and drifting would occur. Matter is like organs and tissues, the physical result of deeper systems at work. Just as organs give physical form to the invisible processes of life, matter provides substance to the underlying structures of reality, making the unseen visible. Without it, there would be no tangible form, only unseen processes without expression. Together, these frameworks form the deep architecture of existence. Each plays a distinct role, but none stands alone. They function as a unified whole, shaping a reality far more layered than it first appears. This complex yet elegantly orchestrated series of seamlessly integrated frameworks renders reality and life possible. Most of these 8 somethings are found everywhere, even in vast cosmic voids. This insight shows that even the most barren regions of space are not truly empty. As far as we know, absolute nothingness does not exist anywhere within our observable reality. Theoretically, true nothingness, the complete absence of mathematics, fields, laws, forces, and matter, would require the elimination of all 8 frameworks. It's not just empty, it's the absence of structure itself. This idea stretches the imagination far beyond our current scientific understanding. To even consider such a state, we must imagine rewinding time to a moment before the universe began, into a realm where none of our known frameworks existed. Yet, let's set that thought aside until we gain a clearer picture of the nature of reality within it. A key part of that clarity comes from understanding that our definition of reality depends on scale, how and where we choose to look. Reality, as perceived through our 5 senses, appears straightforward. Objects are solid, time is constant, and space is an empty backdrop. This intuitive view gave rise to classical physics, most famously formulated by Isaac Newton. Newton's understanding of reality resembled a well-oiled grandfather clock, predictable, mechanical, and governed by equations that could be written with a quill. Mass attracted mass through gravity. Forces acted directly and proportionally. Time ticked evenly for everyone, everywhere. It was elegant, orderly, and immensely beneficial. But then came Albert Einstein, a young patent clerk who dared to question the neatness of it all. He tossed the conceptual equivalent of a monkey wrench into Newton's ticking gears. With his theories of special and general relativity, he revealed that space and time were not separate absolutes, but rather part of a unified, flexible framework, often described metaphorically as a fabric called space-time. Space can bend, time can stretch, clocks can disagree, and gravity? It is not a force, but the curvature of space-time caused by mass and energy. Einstein helped us understand that the universe isn't absolute. It's relative, changing depending on how fast you're moving or how close you are to a massive object. To a distant observer, a second near a black hole passes more slowly than a second on Earth. A meter stick traveling at near light speed appears shorter to an outside observer. Ideas once regarded as philosophical speculation, such as the relativity of time and the interdependence of the observer and the observed, became central pillars of modern physics. As revolutionary as Einstein's theories were, they didn't close the book on the nature of reality. They opened it to a new chapter. In the early 20th century, a new generation of physicists, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others, began to probe even deeper, venturing into the realm of the ultra-small. What they found was not just surprising, it was profoundly unsettling. This effort marked the birth of quantum mechanics, a theory that describes reality not as deterministic but as probabilistic. In this peculiar new world, particles show wave-like behavior, and wave phenomena can produce particle-like results. A particle doesn't have a fixed location but exists in a cloud of possibilities until measured. Measurement plays a role in determining which specific outcome becomes real, collapsing a range of possibilities into a single observed result. Entangled particles can instantaneously correlate their states across vast distances, seemingly defying Einstein's speed limit, though no usable signal is transmitted. Some particles can tunnel through barriers, as though classical rules are mere suggestions rather than strict laws. Outcomes are never guaranteed, only the probabilities of different outcomes can be predicted. In this realm of uncertainty, specific properties such as position and momentum cannot be known precisely at the same time, not because of technological limitations or measurement errors, but as a fundamental limit of nature itself. Suddenly, reality was no longer a fixed external mechanism. It transformed into a fluid interplay of probabilities, fields, and interactions, an ever-shifting sea of potential waiting to be realized. Let's take a step back and gain perspective on the various scales of reality that physics reveals, each one unlocking a distinct layer of how our universe operates. Classical mechanics describes the motion of everyday objects, predictable, tangible, and intuitive. General relativity extends our view to the cosmic scale, explaining gravity, black holes, and the curvature of space-time. Quantum mechanics leads us into the atomic realm, where particles are characterized not as certainties but as probabilities. Quantum field theory builds upon quantum mechanics and special relativity, demonstrating that particles are localized ripples in unseen fields that fill all of space. String theory proposes that all particles are not point-like but are tiny, vibrating strings, offering a bold yet still speculative framework for unifying all the forces of nature. As this table shows, each scale functions within its own domain, governed by distinct principles and characteristic measurements, from the familiar world of meters and seconds to the unimaginably small Planck scale. But this leads to a deeper question. Which of these frameworks reveals what reality truly is? The answer, as always in science, depends on context. The proximity and overlap among these models, illustrated in our bubble diagram, emphasize their interconnected domains and complementary strengths. Newton's laws continue to accurately describe the world under conditions of low speeds and weak gravitational forces. Einstein's relativity is crucial when masses are extreme. Velocities approach the speed of light, or distances extend across cosmic scales. Quantum mechanics governs the behavior of particles and energy at the smallest scales, where uncertainty, superposition, and entanglement dominate, and its predictions have been confirmed with astonishing precision, sometimes to within 1 part in a trillion. Quantum field theory goes even deeper, unifying quantum mechanics with relativity and forming the foundation of the Standard Model, the most thoroughly tested theory in physics. And then there's string theory, a fascinating idea that seeks to unify all the forces of nature, including gravity, within a single theoretical framework. It envisions every particle as a tiny vibrating string. However, despite its mathematical beauty, string theory remains unproven. While it yields theoretical predictions, such as the existence of extra dimensions or supersymmetry, these remain unconfirmed, and the required energies to test them lie far beyond the reach of today's experiments. Its greatest strength, providing a unified framework for all fundamental forces, may also be its greatest weakness. It currently sits at the frontier of mathematics, but well beyond the grasp of experimental verification. So, in this episode, we'll set string theory aside. Not because it lacks value, but because our focus is on the established and testable layers of reality, where the evidence is strongest. This approach allows us to lay a solid foundation, one grounded not in speculation, but in what science can currently observe, measure, and verify. In the next episode, we'll build on that foundation as we explore speculative cosmological models, including some related to string theory. These frameworks challenge the limits of current understanding while remaining grounded in the scientific principles established in this episode. Among the scientific layers and scales we've examined, quantum field theory stands out as one of the most profound theories, unifying particles, fields, and forces into a single elegant framework. Let's focus on this extraordinary model and the insights it offers about the nature of our reality. This model describes reality as a collection of invisible quantum fields that permeate all of space. Like waves on the surface of the ocean, these fields can ripple, interact, and influence each other. In this section, we'll focus on 17 key fields that form the essential structure of the Standard Model of particle physics, grouped into fields associated with 2 categories of matter particles, quarks such as up and down quarks, and leptons including electrons and neutrinos, each having its own quantum field. Fields for force carriers like photons and gluons, and the Higgs field, which uniquely contributes to giving mass to certain particles. To visualize this, picture a serene forest with 17 lightweight stretchable canopies suspended one above the other. Each canopy represents a distinct quantum field. While separate in concept, they coexist throughout space and are subtly connected, anchored by the same trees and swaying in response to invisible tension in the air. Due to quantum uncertainty, these canopies are never completely still. Even when undisturbed, they flutter gently, creating a measurable effect known as vacuum fluctuations or zero-point energy. These subtle jitters persist even in the coldest, most isolated regions of the cosmos and help explain why absolute zero, the complete absence of motion and heat, can never be fully attained. Now picture people lying on these stacked canopies in sleeping bags. When someone shifts their weight or moves, that motion can ripple through the structure, bumping into others and transferring some of that energy. In quantum field theory, this type of interaction is referred to as a localized disturbance, a concentrated energetic event within a field that can, if sufficiently intense, influence nearby fields. The extent of that influence depends on two factors: the amount of energy involved and how strongly the fields are coupled. That is, how easily one field can affect another. Consider the transferred energy as the extent to which someone shifts in their hammock. A slight motion creates only a gentle ripple, while a sudden move produces a larger one. The coupling strength, the ease with which energy is exchanged between fields, reflects how close the hammocks are to each other and how tightly they're connected. If the hammocks are spaced far apart or loosely suspended, movement in one may go unnoticed by the others. However, if they're close together and tightly coupled, even a subtle motion can ripple outward, jostling those above and below. In quantum field theory, this illustrates how fields interact. The more strongly coupled they are, the more energy they can exchange. A small transfer of energy generates only gentle ripples in nearby canopies or adjacent fields. However, if the energy transferred to a field equals or exceeds the field's rest mass energy, the small number listed next to each particle in the standard model, something remarkable can occur. The ripple may give rise to a real stable particle in accordance with Einstein's famous equation, E equals mc squared. What makes this behavior so extraordinary is that in quantum field theory, all particles, including the matter that forms our reality, emerge as localized excitations in their respective quantum fields. Without these underlying fields and their ability to be excited, matter as we understand it could not exist. If the energy falls short of that threshold, the ripple simply fades away. No lasting particle forms. It's just a brief fluctuation, a ghost of a possibility that vanishes almost instantly. Take the electron field, for example. It must be excited with at least 0.511 megaelectron volts of energy to produce a real electron. A ripple with only 0.5 MeV? Not enough. If the energy exceeds the threshold significantly, it may generate multiple particle-antiparticle pairs, depending on conservation laws such as energy, charge, and momentum. Some fields, however, do not require any threshold at all. Massless particles such as photons and gluons can be created from even small amounts of energy. This is one reason light is so frequently emitted throughout the universe. A photon can emerge even from a tiny energy shift, like those caused by atomic transitions. But while photons can travel freely through space and mediate long-range forces, gluons behave very differently. Although they are also massless, gluons carry a color charge, which leads to strong interactions among themselves. This results in a unique phenomenon known as confinement, a property of the strong force that prevents gluons and the quarks they bind from existing in isolation under normal conditions. In this video, the translucent orbs represent hadrons, such as protons and neutrons. The colored spheres symbolize quarks, while the springs connecting them illustrate gluons. Confinement ensures that these components remain permanently bound together, creating the composite particles that constitute atomic nuclei. Let's now connect the standard model of particle physics with the four fundamental forces that govern all activity in our universe, visually illustrating how particles and forces interrelate. The standard model is the most successful framework we've developed for explaining how the universe operates at the quantum level. It is to particle physics what the periodic table is to chemistry, a map of the fundamental building blocks of matter and the rules governing their interactions. It categorizes particles into two major families. Fermions, represented in purple and green, are composed of quarks and leptons. These serve as the fundamental building blocks of matter. Everything we observe, atoms, molecules, stars, and living organisms, is made from these particles. Bosons, depicted in red and gold, act as the force carriers. These aren't mere theoretical constructs. They're actual particles exchanged between fermions to facilitate the fundamental forces of nature. At the heart of this framework are four fundamental forces. Gravity affects how mass and energy bend the fabric of space-time, causing objects to be pulled toward each other. Although it is not yet part of the standard model, it remains one of the four fundamental forces that shape the universe. Electromagnetism controls the interactions between charged particles and underlies electricity, magnetism, and light. The strong force binds quarks together to form protons and neutrons and holds those nucleons tightly within atomic nuclei. The weak force drives processes such as nuclear decay and the fusion reactions that power stars. To better understand how these categories relate, let's use the analogy of a baseball game. The fermions are akin to players on the field. There are two teams, particles such as electrons, quarks, and neutrinos, and their mirror opposites, antiparticles such as positrons, antiquarks, and antineutrinos. Each one has a role, and together they create the substance of the game. Bosons are similar to baseballs, the objects that enable players to interact. Without baseballs to throw, catch, or hit, players couldn't interact. Similarly, fermions couldn't interact without bosons, and the universe couldn't function. The four forces are the rules of the game. Electromagnetism resembles the ability to throw, hit, and catch, enabling everyday interactions among players. The strong force is comparable to the coordination among infield players, binding them tightly together for close, rapid plays. The weak force is like the rules that allow substitutions and role changes, transformations that may seem subtle but change the course of the game. Gravity serves as the playing field itself. It shapes how the ball arcs, how players move, and how everything stays grounded. It defines the arena, even though we seldom think about it. Returning to our diagram, we can now link each force to its respective boson. The photon mediates the electromagnetic force. The W and Z bosons mediate the weak nuclear force. The gluon mediates the strong force, quantum chromodynamics, that binds quarks together inside protons and neutrons. The strong nuclear force, which holds protons and neutrons together in the nucleus, is a residual effect of this fundamental force. And finally, there's the Higgs boson, highlighted in gold. It's connected to the Higgs field, which is responsible for providing mass to other particles. This happens through two mechanisms: Yukawa coupling for quarks and leptons, and electroweak symmetry breaking, which gives mass to the W and Z bosons. Without the Higgs field, these particles would remain massless, and the universe would lack the structure necessary for galaxies, stars, planets, or life. Together, the Standard Model and these fundamental forces form the backbone of modern physics, not only describing what everything is made of, but also illustrating how everything interacts and holds together to create the vast dynamic universe we observe. If you were paying close attention, you might have noticed something strange. None of the bosons we've discussed account for gravity. That's not an oversight. It's a glaring gap in the Standard Model. Unlike the other fundamental forces, gravity doesn't fit neatly into the framework of quantum field theory. It remains a mysterious outlier. While electromagnetism, the weak force, and the strong force are all explained through quantum fields and particle exchanges, gravity is still described by Einstein's classical theory of general relativity. If gravity is a force like the others, it should have a corresponding force-carrying boson. Physicists have even named this hypothetical particle the graviton. But here's the catch: no one has ever detected a graviton. That's not particularly surprising, though, because gravity is by far the weakest of the four forces. It is weaker, in fact, by a factor of trillions compared to the next weakest force. A small magnet can lift a paperclip against the full gravitational pull of the Earth, demonstrating how weak gravity is on small scales. Some theoretical estimates suggest that detecting a single graviton would require a detector so massive and sensitive that it could collapse under its own gravity, potentially forming a black hole. In other words, any instrument powerful enough to observe a graviton might be destroyed by the very force it aims to detect. This is just one of many ways the universe appears designed to keep some of its deepest secrets just beyond our reach. Yet if gravity is so weak, why does it feel so powerful? Why does it dominate the movement of planets, shape galaxies, and govern the structure of the cosmos? The answer lies in scale, a recurring theme in this episode. The other forces primarily operate at subatomic distances and often cancel each other out due to opposing charges or limited ranges. Gravity, however, has an infinite range and acts on everything with mass or energy. It is always attractive and additive, never neutralized or shielded. Unlike the other forces, gravity never turns off. It simply weakens with distance. If gravity were as strong as the other forces on small scales, the universe as we know it couldn't exist. Stars would burn too quickly or implode. Galaxies wouldn't form elegant spirals. They'd fragment or collapse. Planets might never coalesce, and life as we understand it would be impossible. Ultimately, it might be gravity's gentleness, not its strength, that made life possible. It's a force so patient and persistent that it holds the fabric of the universe together, quietly shaping reality without overwhelming it. Perhaps the most familiar way to visualize how invisible fields work stems from a simple childhood science experiment. When you sprinkle metal shavings on a surface and bring a magnet nearby, the shavings begin to shift, forming graceful arcs that reveal the shape of the magnetic field. Although the magnet never touches the shavings, its influence extends across space, pulling, shaping, and organizing without direct contact. While magnetic fields are classical in nature, this provides a glimpse into how quantum fields behave. Just as magnetic fields shape metal shavings from a distance, quantum fields govern particles, guiding everything from electrons in atoms to fusion reactions in stars. Although structures like galaxies are largely shaped by gravity, their components arise from the quantum fields that underlie matter. In quantum field theory, particles are the energetic signatures of fields revealed through their interactions with matter or measuring devices. Much like wind made visible by rustling leaves, quantum fields reveal themselves when their fluctuations manifest as particles. The fields serve as the hidden framework of reality, while the particles act as their tangible expression. There's another piece of the puzzle that radically reshapes our understanding of matter itself. So far, we've described the quantum world as consisting of discrete particles and force carriers. Let's revisit the atomic structure to gain further insights. Atoms consist of protons and neutrons in the nucleus, with electrons orbiting around them. Protons are made up of 2 up quarks and 1 down quark, while neutrons contain 1 up quark and 2 down quarks. These quarks are bound together by the strong force mediated by gluons, the quantum particles exchanged among quarks. You will recall that gluons resemble baseballs being rapidly passed between the quarks, maintaining their tight binding inside the proton with remarkable strength. However, the quantum world doesn't draw such clear lines. There's a gray area between mass, motion, and interaction where those distinctions start to blur. Consider the proton. We know it has a mass of about 938 megaelectronvolts. However, if we sum up the known mass of its constituent quarks, 2 up quarks, each about 2 megaelectronvolts, 1 down quark, about 5 megaelectronvolts, that gives us a total of just 9 megaelectronvolts of mass. This accounts for less than 1% of the proton's actual mass. So where does the remaining 99% come from? This is where quantum physics unveils its deeper layers. The missing mass of the proton doesn't stem from the quarks themselves. It emerges from the energy of their interactions. Within the proton, gluons are constantly exchanged, not only binding the quarks, but also creating a dense sea of quantum activity. These interactions give rise to fleeting quark-antiquark pairs and gluon fluctuations, all of which contribute to the proton's internal structure. Physicists often refer to these as virtual particles. However, in this context, they represent real measurable effects of the quantum vacuum. This constant exchange of energy, tension, and motion creates a dynamic internal environment. And thanks to Einstein's equation, E equals mc squared, all of that energy manifests as mass. In this way, the proton is heavy not because of what it contains, but because of how intensely it holds itself together. Even when it appears still, its interior is a storm of interactions, so energetic that their cumulative effect results in mass. And that leads to a profound insight. Most of what we call matter is not solid stuff. It is energy in motion, structured by invisible fields and bound by fundamental forces. Even the most familiar objects, your hand, a mountain, or the earth itself, are composed of atoms that are mostly empty space. The mass of those atoms does not arise from the weight of their components, but from the pressure and tension within quantum fields that are always in motion. Reality isn't constructed from small blocks. Rather, it's shaped by connections, vibrations, and energy, intertwined like the strands that make up a rope. Let's examine some numbers to help us understand the staggering energy hidden within matter, from subatomic particles to everyday objects. Since we previously used a paperclip to illustrate gravity's weakness compared to electromagnetism, let's now ask how much energy is stored in a single paperclip according to the equation E equals mc squared. This equation informs us that energy equals mass multiplied by the speed of light squared. The speed of light is approximately 300 million meters per second. Squaring that results in about 90 trillion meters squared per second squared. A standard metal paperclip weighs about 1 gram or 0.001 kilograms. If its entire mass were converted into energy, as happens in matter-antimatter annihilation, it would release approximately 90 trillion joules of energy. To put that in perspective, the energy in a single paperclip could power the entire United States for approximately 6 seconds, boil over 11 million gallons of water, or fully charge 1.7 billion smartphones, or release more energy than the atomic bomb dropped on Hiroshima, which unleashed about 63 terajoules. That's the staggering potential contained in just 1 gram of matter. While we don't yet have the technology to unlock all that energy, Einstein's equation reveals how deeply mass and energy are intertwined. The energy released in nuclear reactions, such as fission and fusion, comes from changes in nuclear binding energy, which result from the residual strong nuclear force acting between protons and neutrons. Although only a small amount of mass is converted into energy, it is enough to power stars or destroy cities. This indirect transformation remains grounded in the strong interaction, the force that binds quarks within protons and neutrons and, through its residual effects, holds atomic nuclei together. That's why nuclear power and atomic bombs, even though they harness only a small part of matter's full potential, release such incredible energy. They offer a glimpse into the immense power hidden within ordinary matter. Now let's scale up. The total energy contained in all matter in the observable universe is estimated to be around 9 times 10 to the 69th joules, a 9 followed by 69 zeros. It's a number so vast that it defies comprehension. And yet, that's the energy that came into being with the birth of the universe. What can we learn from these insights into the functioning of our universe at the quantum level? A paperclip isn't merely a piece of bent metal. It's a storm of bound energy, structured by quantum fields, stabilized by fundamental forces, and concealed beneath the illusion of solidity. The nature of reality might not exist solely in matter, but in structure, not in isolated entities, but in the relationships that connect them. From the subtle movement of quantum fields to the gravitational arcs of galaxies, the universe seems like a broad quilt of connection, a unified whole where each thread depends on every other. If reality's ultimate identity is relational rather than substantial, then meaning itself may be discovered not in the parts, but in the patterns, in the harmony of interactions that connect existence. This view suggests that being is not defined by independence, but by interdependence, a coherence that arises from relationships. If relationships give reality its shape and coherence, what does this suggest about existence, consciousness, and the deeper meaning behind everything? And this leads us to an even greater mystery. If this is how reality functions, why is it that way? Why a universe based on uncertainty, entanglement, and mathematical symmetry? Why a reality where particles flicker into existence from hidden fields, where empty space buzzes with energy, and where the act of measurement influences which outcomes become real? What started it all, and why is there something rather than nothing? It is at this frontier where physics grasps the known with one hand while reaching toward the unknown with the other, that science encounters metaphysics and reason yields to reflection. Here we begin to question whether the universe's deep structure suggests not only order but also meaning. One of the most fascinating aspects of science is that each answer leads to even deeper questions. It is a recursive process. Every mystery solved opens a door to greater complexity, like stepping through one door only to find a corridor filled with more doors, each offering a new frontier of understanding. Will we ever reach a point where all questions are answered? And if we do, would that mark the end of science or the beginning of intellectual stagnation where curiosity fades and the thrill of discovery is replaced by a quiet sense of finality? Is it the pursuit itself that gives science its meaning? From this view, the universe's infinite complexity isn't a problem to fix, but a gift to explore, an open-ended call to wonder, awe, and endless discovery. Our search for answers to these questions and even deeper mysteries has only just begun. Join me for the next episode as we continue our investigation. In the upcoming episode, we will explore the point where cosmology intersects with causality and where the nature of beginnings might reveal clues about the meaning of existence itself. Thanks for joining me on this little adventure. I'm glad you watched all the way through, and I hope that means you found it insightful and enjoyable. Since I did all the work myself, it took me 3 months working full-time. So I decided to have a bit of fun and list all the various hats that I wore in the closing credits. If I get enough subscribers in the future on this new channel, I hope to outsource some of those roles so that I can publish more frequently. And on that note, I hope I've earned your subscription so that my future work gets presented to you. Your likes, shares, and subscriptions are what make it possible for me to continue making documentaries like this one. Thank you so much for your support and help launching this new channel. If you'd like to play more of an active role in the creative process, join me over on my Patreon channel, where you'll have the opportunity to provide your feedback and insights on work in progress and help shape each documentary. Until next time, stay curious, my friend.